In section 14.5, we're looking at laws of logarithms, and the idea is we've just invented this, well not invented, we've just been introduced to this new algebraic idea of a logarithm, and what we always do is we try and look at the rules and how we can play with the rules and what we can do with the new information that we've got. And the rules of logarithms, there are three of them that we are going to want to know, which you can see on page 321. We call the multiplication law, the division law, and the power law. And then there are some extra little facts as well, which aren't really, well, they refer to them as special cases, and we'll get to those in a second. But really, there are three rules of logarithms which we're going to use in algebraic sort of ways. And remember that logarithms are kind of a reflection of powers, right? So if I get if I get a to the power of m, and I've got a to the power of n, and I times those two things together, I get to the a to the power of m plus n. Okay, we know that rule from indices, right? So can I come up with a logarithmic sort of version of this? So let's take our a to the power of m, and let's take our a to the power of n, and let's think of those as logarithms. So this one we will call x, and this one we'll call y. And that means log to the base a of x equals m. This means log to the base a of y equals n. Okay, those are the equivalent statements like we talked about in section 14.4. So if I now do a to the m, a to the n is a to the m plus n, that's the same as doing x times y, okay? So xy equals a to the m plus n. But if I now take logs of this side, well, that's log to the base a of xy. And this is log to the base a of a to the power of m plus n. Well, log to the base a of a to the power of something, well, that's just going to be m plus n, right? Because think of rules of logarithms, the definition of logarithms, a to the power of what equals a to the power of m plus n? Well, the answer is going to be m plus n, isn't it? So m plus n, well, m was log to the base a of x, and n was log to the base a of y, and that gives us our rule, which is, that's the derivation of our rule, and now we can just use it from now on, which is that, okay? So if I've got log to the base a of two things times together, log to the base a of the first one plus log to the base a of the second one. And can you see that with logarithms, we have the same idea as with indices, that there's a sort of link between multiplication and addition. So the multiplication here becomes an addition here, the multiplication here becomes an addition here, and we've got to be careful. Sorry, you couldn't see that, could you? So the multiplication here becomes an addition here. The multiplication here becomes an addition here, okay? So that's our multiplication law for logarithms. The division law comes from the back of that. So if I got log to the base a of x divided by y, I could think of that x divided by y as x times y to the power of minus 1. And I can think of, so log to the base a of x y to the minus 1 is log to the base a of x plus log to the base y to the power of minus 1. Now, that's as far as we can go with it at the moment. So there's our multiplication law. The division law at the moment is going to stop and look like this. Let's just have a look at the power law. Log to the base a of x to the power of something. Well, let's think of that as log to the base a of x to the power of 3. So x times x times x. Well, through our multiplication law, that is log to the base a of x plus log to the base a of x plus log to the base a of x. So that is 3 log base a of x. So log base a of x cubed equals 3 log base a of x. And I know I'm only proving this for integers, but can you see that whatever the integer is there, I get log to the base a of x to the power of n is n times log to the base a of x, just as a consequence of the multiplication rule. Okay, so we have this fact as well. That's our power law. I've demonstrated it for integers, and I'm just going to ask you to trust me for numbers that aren't integers just for the moment. You can stop and think about it for a while yourself if you want, but just to try and get through the video, we'll stop there. Now, if I take this power rule, I can bring this minus 1. It's y to the power minus 1. I can bring it out here to the front, and I can say log to the base a of x, take away log to the base y. Okay, so log to the base a of x over y is log to the base a of x, take away log to the base a of y. So those are the rules, and that's where they come from. Okay, and they're written out more neatly for you on page 321. The three special cases, let's just deal with those quickly. Log to the base a of 1 over x is log to the base a of x to the power minus 1, which by the power rule is minus log base a of x. Log base a of a, well, this is, if you just think about this, a to the power of what equals a? Well, that's a 1, isn't it? Okay. Just think about the rewriting this as powers. A to the power of 1 equals a, right? That thing to the power of that thing equals that thing. That's the definition of what a logarithm is. So log to the base a of a is always 1. If the base and the thing you're taking the logarithm of are the same, then you're always going to get a 1. And log to the base a of 1, well, let's think about this. Log to the base a of 1 is something. Well, that is a to the power of that something equals 1. So what's that something got to be? It's got to be a 0, hasn't it? Okay, a to the power of 0 is always 1. So those two little rules there are just using backwards our indices rules that we should be nice and familiar with. Okay, so those are the rules that we can now play with, and of course, as with any bit of algebra, we've got some new facts, what a logarithm is. We look at what those new facts tell us, and we develop a few rules, and now we just got to apply them in a lot of different contexts. I obviously can't show you every possible example, but I'll just pick one or two from the examples that are there. So if I pick, let's just do the simplest one they've got just to get us warmed up. Log to the base 3 of 6 plus log to the base 3 of 7. The bases have to be the same on the logarithms. Same as with indices, the bases have to be the same, don't they? If you get x to the power of 4 times x to the power of 5, then you can use the indices rules to make that x to the power of 9. If you get x to the power of 4, y to the power of 5, there's nothing we can do with that. Same here, the base has to be the same. So we've got two logarithms added together. So that is log to the base 3 of 6 times 7, okay? Which is 42. We don't know what log to the base 3 of 42 is, but we know log to the base 3 of 27 is 3, log to the base 3 of 81 is 4. So a number between 3 and 4 would be the answer. If we wanted to find it, we'd type it in the calculator. But it's not asking us to find it, it's asking us to write as a single logarithm, so we'll leave it there. Let's have a look at part C. 2 lots of log to the base 5 of 3 plus 3 lots log to the base 5 of 2. Well, by the power rule, I can take the number from the front here and bring it up. So log to the base 5 of 3 to the power of 2 plus log to the base 5 of 2 to the power of 3. Okay, so I can bring those things up there. And now I can use the multiplication law, log to the base 5 of this thing plus this thing. So that is log base 5 of, well, 3 squared is 9, 2 cubed is 8, so it's log base 5 of 17. Okay, that's the end of the question, but again, it's helpful to, oh dear, hang on a minute, sorry, what have I done? Oh, I've made one of the classic mistakes, that isn't an addition there, it should be a multiplication here, so 9 times 8 should be 72. Silly me, right, there we go. Now, that's the end of the question, but it's always helpful to just try and get you sort of familiar with what you're dealing with. So just for the sake of that, 5 to the power of 2 is 25, 5 to the power of 3 is 125, so log to the base 5 of 72, if I put that in a calculator, would be somewhere between 2 and 3. It's going to be 2 point something. One other thing that is worth pointing out here is that this log rule is for log of xy turns into log of x plus log of y with all the bases the same, okay? Where people start going wrong is that you end up with a question and you've got log of x plus y, something added together here, and you think, well, there is a rule to do with logarithms and turning additions into multiplications, and it would be much easier if I had log base a of x times log base a of y, and you try and switch things around there. Or if you've got two logarithms multiplied together and you want to turn that into something here, and just be aware that you get the multiplication is here and the addition is there. So it's actually the mistake I made here, wasn't it? I've got an addition there and I left it as an addition. Well, that addition needs to turn into a multiplication. Very easy to make that mistake, as I've demonstrated. And I'll do, these are now spelled out for you, I think, in the examples. Let's do one from example 11, just in case anybody's still watching. So if I've got log base a of x root y over z, that looks like a nasty one, and it asks us to write these in terms of log base a of x, log base a of y, and log base a of z. So I can use the division rule. I can use the multiplication rule. I can use the power rule here, because y to the power of a half is the same as square root of y. So I get log base a of x plus a half log base a of y minus log base a of z is equal to that thing there. Okay, so we can split it up like that. It's just remembering those three rules, look at the question, try and solve each one of, try and apply each of the rules and see which one works. I said that with the last one, but let me just have looking at it, example 11, 12 and 13 are slightly different. They are asking us to solve equations, so just so that I'm not missing anything else, I'll do example 13, log base 3 of x plus 11, take away log base 3 of x minus 5 is equal to 2. Well, I can simplify this because I notice they've got the same base, so I can use the division rule. X plus 11 over x minus 5 is equal to 2, log base a of that. Now, I've now got log base of something equals 2. So, in other words, that thing to the power of that thing equals x plus 11 over x minus 5. Okay? And we can work from there. Sorry, it's not an a, is it? It's a 3. So 3 squared. And that's now an equation that we can solve, all right? The other way of thinking about that is if I've got log base 3 of x plus 11 over x minus 5 is equal to 2. Well, if I do 3 to the power of this side, 3 to the power of 2, and if I do 3 to the power of this side, well, then I'm going to have 3 to the power of log base 3 of x plus 11 over x minus 5. Well, 3 to the power of log base 3, they're inverse operations, aren't they? So those ones cancel out, and I'm left with x plus 11 over x minus 5 equals 3 squared. And either way, that is now an equation that we can solve. We'll see more about solving equations in the next section, but that's it for 14.5.